Biostat 66111, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Welcome to another lecture for Biostat 6611. We'll be talking in this lecture about continuous distributions, the expected value, variance, and standard deviation, and this will serve as the analogous set of slides for the discrete distributions lecture from week 2. We'll first again review random variables, touch on PDFs and CDFs in the context of our continuous random variables, and then do some example calculations for the expected value, variance, and standard deviation. So as we review from last week, random variables and probability distributions are the theoretical or mathematical representations of data values in the frequency distributions. So a random variable is some variable whose value depends on some random phenomenon or sampling. Possible values then represent the possible outcomes of some future yet to be performed experiment or sampling. We're going to call these possible values then the sample space, or things we could potentially observe. And like last week, capital letters will represent a random variable and lowercase letters will represent a realization or an observed value of the random variable. So we saw last week the probability distribution described the probabilities for both the discrete random variable through a probability mass function, but also we hinted at the probabilities for some range of values for a continuous random variable, or the probability density function we'll be talking about today. And these are useful tools, as we'll see. They'll be the underlying concepts behind many of the things we'll be taking advantage of throughout the semester, even if we don't directly involve the PDF or PMF. So continuous random variable. In this case, the sample space is an interval or some continuum with infinite possible values, and we'll see an example of what that means in a few slides. But this is in contrast to the discrete random variable, where we had something that was finite or countably infinite, where we could observe some fixed number of observations. For a continuous random variable, an example might be the height of individuals in Denver. The possible outcomes may be anything in the interval from 0 to 2.72 meters. Realistically, it'd be a little above 0, and 2.72 is the old Guinness Book of World Records max height achieved. But we can imagine that seems to be a reasonable window then of heights we might observe. So we could observe anything in that range from 2 meters exactly to 1.3212 meters, or any infinite combination or value between those. We characterize these continuous random variables by our probability density function, or PDF, the similar idea of the PMF for the discrete. This is a function that gives the probability that x is a value that falls in some range of the sample space. So some example notation we see here, using a little bit of a new notation potentially, we see here we have this variable or symbol for in, so we're saying the probability that x falls within some interval c to d, or written analogously in our probability terminology, the probability that c is less than or equal to x, which is less than or equal to d. And really what we're going to see is that probability of that interval is going to be some function that is dependent upon the given interval. And that interval should be something that's in the sample space of feasible values. So for example, in our height example, if I said what's the interval from -1 to 0, we would know that's infeasible because we would have negative heights. So to help illustrate this idea of an infinite range of possible values for a continuous random variable, let's look at this idea that the probability at any specific value of a continuous random variable is 0, or the probability that x equals some individual specific value x, lowercase x, equals 0. And we'll see this proved a little later with an actual slide and problem using some calculus. But to motivate our intuition, let's start with an idea here where we have a discrete random variable that's uniformly distributed. So we have values at 0 and 1, let's say. We have just two possible observed values. Well, if it's a uniform distribution, what we know is that each one of our bars has a half chance or probability of being selected. Now let's say we were keeping with our uniform distribution, but we wanted to break it down into maybe some additional points within our range here. So maybe we see that we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 0 up to 1 still, but now we can also observe maybe something that's 1/10, 2/10, and so on. In this case now, we actually have increased the potential number of our observed observations. And so we see here that we have a total of 11 different possible choices. So we've divvied up that space further. Well, what if we took each one of these windows or bars again and broke it into 10 more possible selections and 10 more beyond that? What we start to see is that we're going to get some observation or some distribution where we get infinitely smaller possible selections here, to the point where we will have essentially 1 over infinite number of choices, which is going to be equal essentially to 0. So the probability of choosing any one random variable value in a continuous range is essentially 0, unlike in our sort of most extreme version of our discrete random variable at the top, where we had a half or 50% chance of selecting either one. This may make a little more sense when we actually see some more graphical representations of PDFs and CDFs, as well as other distributions throughout this week and the rest of the semester. So the PDF. So again, we're going to let x be a continuous random variable, and we're going to let lowercase x represent the possible values that our random variable x can take on. The PMF of the discrete random variable does not apply to our continuous random variable again. Instead, we denote the function that assigns probability values to our random variable has some function f of x dx. In other words, connecting that to our definition below, which will tie into the integral from calculus. Therefore, we can note if we have an interval of interest, or potentially the entire sample space even, the probability distribution of x over some interval a to b will therefore be represented here by the integral from a up to b of that function with respect to x over that range. And it could be, again, a subset of the overall sample space or the total sample space. But we can note some similar conditions must be met. F of x must be greater than or equal to 0 at all points of the sample space. So much like the PMF, we can have negative probabilities. We can have a probability of essentially 0, but not actually a negative chance. Similarly, if a to b is the range of the entire sample space, the integral then from a to b of f of x dx must equal 1, or in other words, the area under the curve must sum to 1. As an example, we have essentially a normal-like distribution plotted here, and we see an example of what the PDF and intervals may look like and a connection to the cumulative distribution function. Here we're looking at the probability that x falls between an interval of a up to b, and so we see here the first way we can write that is, what's the probability that a is less than or equal to x, our random variable, that is also less than or equal to b. Now, one of the ways we can tie this back to the cumulative distribution function we'll touch on the next slide is that we can break this out into two different calculations. We can look at, well, what's the probability that x is less than or equal to b? In other words, if we look at our actual figure here, if we do everything to the left of b, so going all the way down to negative infinity, and subtract from that the area that we should actually not have shaded in because it's excluded right here, for the probability that x is less than a. This equivalently can be thought of as the CDF values of our capital F of b or capital F of a at the location of b or a, which we'll see on the following slide. So the CDF is the cumulative probability distribution of our function x, or excuse me, our random variable x. In this case, our notation, as we saw on the previous slide, is that we'll use a capital F to represent that function. And many times if we have maybe multiple random variables or distributions at play, we may also wish to add that subscript we see right there, just to help us note that it is specifically being the CDF with respect to x, our random variable. But if we have some particular value a that we want to see what the cumulative probability is at that point, we could write capital F sub x of a, which is really like saying the probability that x is less than or equal to a, which is also equivalent to saying, well, let's just do some calculus and take the integration from negative infinity, or whatever the smallest value may be for our sample space, and integrate up to that value a for f of x dx. In other words, the area under our curve. And so we can see that at the figures on the right-hand side, where the top is again the display of the PDF on the previous page, but we then see below our CDF here, where we have the same value a, and we can then sort of note that it's about 60% of the probability is less than or equal to a. A few other facts of the CDF that relate directly to the discrete distributions we saw before. The CDF is a monotone increasing function where at its smallest possible value it's equal to 0 probability, and at the largest possible value it's equal to 1, which is potentially negative infinity to positive infinity. The CDF and the PDF are also directly related through the first derivative of the PDF, or excuse me, of the CDF with respect to x to calculate our PDF. And we'll see an example of how to do this on a following slide. One of the useful things to know about the CDF, and we're not necessarily going to explicitly refer to this going forward, but every time we execute a statistical test or determine a p-value or some level of significance, we're really using the CDF of a relevant continuous or potentially discrete random variable to come up with that p-value. Because again, we're looking at the probability of something that's at or less than or potentially greater than some given value such as a on the slide here. So let's walk through some calculation examples of a PDF in a more toy context. We're going to assume that x is a random variable that has a PDF f of x equals 2x. So pretty simple construction here, and the sample space is just between 0 and up to 1. Here we're going to try plotting what the PDF would look like, and then we're going to check that it is in fact a valid PDF. I encourage you to pause your video and try sketching out the PDF now, and also checking that it actually is a valid PDF before we go through it together in a second. Okay, let's first sketch out a very simple case of what this PDF might look like. Again, it's not going to be the most exciting of PDFs, but we can note here that we have essentially 0 up to 1 of our sample space. On our y-axis, we'll have 0 up to 2. And we can note here that the PDF is literally just a straight line going from 0, 0 up to 1, 2 for the coordinates. Now, the next step would be to plot, besides plotting the PDF, is to check that it's a valid PDF. In other words, we see if it sums up to 1 in the area under the curve. And so we can do that here with our calculus to say if it's 0 up to 1, it's full range of the sample space, 2x dx. If we integrate this value here, we'll see that we should have x squared, evaluate it from 0 up to 1. This then is equal to 1 squared minus 0 squared, or a value of 1. Therefore, we can conclude that it is a PDF, and we can also identify that the probability in our sort of trivial example here never goes below 0 or as a negative value, or a negative probability. So for part 2, let's consider that same PDF with that same sample space for observed possible values, and let's try to answer the question, what is the probability that x falls between 0 and 0.5? And so again, I encourage you to pause the video here and try this for yourself, and then we'll walk through it together in a second. Okay, let's walk through the question of the probability that x falls between 0 and 0.5. So there's a couple ways we can do this. We can write our probability statement. We could have also noted here that 0 is in fact the lower bound of our sample space, and we could have just said x less than 0.5. But here we can just do this for completeness, since it's going to be correct regardless of if we include or don't include that lower bound. Then we can note here that we will look at the range of values from 0 to 0.5, and then we will write our PDF 2 of x dx here. And so what we want to do again is to see what's that probability that x would fall in between 0 and 0.5. So we'll do our integration, very similar to what we saw in the last slide, because we just have x squared, but now instead of 0 to 1, it's 0 to 0.5. And if we plug in that value, we have 0.5 squared minus 0 squared. And so we see that the probability here is 0.25. Or in other words, if we, again, just sort of sketch out that PDF, we can note that 25% of our distribution will fall below 0.5, and 75% will be falling above 0.5 up until 1. For part 3, let's consider again the same PDF. In this case, we can just state as a fact the CDF for this distribution is capital F of x equals x squared. So let's just check that relationship with the PDF, where the first derivative of the CDF should be equal to our PDF. Again, feel free to pause the video here and we'll walk through it together in a second. Okay, let's just verify that we take the first derivative, d of dx, with respect to our CDF of x squared here. We can then see that indeed this is a not super exciting example where it does take the first derivative to be equal to 2x, which is the distribution of our PDF. You'll also note if you're taking theory this semester or in the future, you'll learn more about how you can identify as well from the PDF to calculate the CDF or identify different terms that might be needed to make sure the CDF does actually derive to the PDF in a problem. Okay, part 4. Consider the PDF again, f of x equals 2x. X is between 0 and 1. What is the probability that x is exactly 0.5? So remember from earlier, we noted that it should just be equal to 0. We had our sort of toy example where we imagined if we kept slicing our uniform graph into further smaller and smaller slivers, eventually we could have infinite slivers, so 1 over infinity. Another way we can prove this is, though, just by writing the calculus out. So if we want to know the probability that x equals exactly 0.5, we can know this is equivalent to writing our integral from 0.5 up to 0.5 of 2x dx. What we can note here then is that if we finish this out just for completeness, we're really just subtracting the number from itself. So we have 0.5 squared minus 0.5 squared, which is equal to 0. Therefore, further reinforcing that when we're looking at these continuous distributions, it doesn't really do us use to look at a single value, but rather a range of values, even if that range was a small range, such as 0.049 to 0.051. At least we'll have some mass at that possible range of values. So that represents the idea of PDFs, CDFs, and some of the calculations we can do if we know them. Another thing we want to see is the complements to the discrete version of the expected value, variance, and standard deviation. Here I'm just stating the formulas because we're going to walk through some examples and you'll do some on the homework, but for the most part we're going to take advantage of the fact that these named distributions will have already identified and known expected values and variances that we can just take advantage of instead of having to calculate by hand each time. We can note that we have some similar setups to our discrete distributions where the expected value is going to be whatever the value of our realized value lowercase x is with multiplied by its f of x dx term, or the PDF component, and that'll equal our mean mu. The variance similarly will be our value x minus the expected value above squared times the PDF. However, we will note that it's oftentimes easier to use the computational calculation, where we can calculate e of x squared in addition to the quantity e of x, which we then square. And just like before, the standard deviation is equal to the square root of the variance. To help illustrate these, we'll walk through some examples of calculating them with respect to our toy value we had earlier. So again, consider that PDF f of x equals 2x, where the range of support is 0 up to 1. What is the expected value e of x? Now again, I encourage you to pause your video, and we'll go through this together in a second. Okay, we have it started here with the definition on the slide. The expected value of x is equal to the integral from, generically speaking, or in general, negative infinity to positive infinity, x times f of x dx. In actuality, we'll want to put in our actual range, 0 to 1 in this case, of the sample space, and then we'll put x times 2x dx. We can then recognize this is really just 2x squared dx, looking at the integration now of just, instead of just 2x, 2x squared. We can then see here, if we do go through and actually take this integration, we should arrive at 2x cubed divided by 3 from 0 up to 1 is where we're evaluating. At this point, we'd have 2 times 1 to the cubed divided by 3 minus 2 times 0 cubed divided by 3. Or really what we see here is, because we chose for this example nice values like 0 and 1, we actually have an expected value of 2/3, which we can also think might make some sense when we think back to the probability that x was less than or equal to 0.5, because that only included 25% of the area under the curve. So if only 25% of the values were possible at the lower range, the expected value, or the point where half of the data might be observed, would probably be above that range. Now let's look at an example with the variance. And as I mentioned, it's oftentimes easier to calculate with the computational form. And so that's what we're going to walk through here. So I encourage you again to pause your video and try calculating that out by first deriving e of x squared, and then using the 2/3 we calculated previously. But you can also apply the formula we had in the previous slide as well to see that they do match. I'll give you a second to pause your video before we continue. Okay, so let's first calculate that e of x squared value. And so we'll see here it's very similar idea to what we had previously. Instead of just x times f of x dx, we're going to actually plug in x squared, and then we'll plug in our 2 of x dx. Again, we can write out our integral of 0 to 1, make it a little nicer to combine the like terms, where we see we have 2x cubed dx. So now if we take our integration here with respect to x, we will see that we have 2x to the 4 divided by 4, evaluated at 0 to 1. We can rewrite this as x to the 4 divided by 2, 0 to 1, which is equal to 1 to the 4 divided by 2 minus 0 raised to the 4th power divided by 2, or 1/2. Now, don't forget we can't actually stop here. We have to go back and plug this into our formula for the variance of x. But we see here that we'll have 1/2 minus our 2/3 from the previous slide, which is going to be squared based on our formula. So we really have 1/2 minus 4/9. In this case, we can get them to have our common denominator, so we can actually see how the numbers work together, these two fractions. So we have 9/18 minus 8/18, which means that our variance will be equal to 1 over 18. And again, you can verify this if you want, using the calculus and integrating x minus mu times f squared times f of x dx. So that wraps up this set of lecture slides, and here's just a review of the formulas for our random variables. We have the discrete on the left and the continuous on the right, so you can more readily see the similarities and subtle differences where discrete involves summation and continuous involves integration. And again, we'll see this pop up a few times throughout the semester, but a lot will be relying on previously shown and proven properties. But now you have the information and knowledge to know where they come from and how you could calculate them yourself.